From Diamond Light Source, this is the Diamond Podcast.
This month, we get creative and get a new insight into the light source. We dive into a fictional world where aliens walk the Synchrotron, dementia is diagnosed on site, and a major outbreak threatens our lives.
I don't know how long I have. I'm recording this to get 3 very important messages out. Message 1, this virus, disease, it has other transmission vectors other than human bites. Message 2, along with this recording there are a series of data files from the beamline at Diamond to determine what you're going to be dealing with.
And to hear message 3, keep listening. But fear not, the staff of Diamond are perfectly safe. But we'll be hearing the inspiration behind this story later in the programme, as well as investigating potential new diagnosis methods for Alzheimer's disease, progress in the fight against plant pathogens, and all the latest research news and events from Diamond, including a new method of carbon capture. Hello, I'm Mira Senthilingam, and this is the November edition of the Diamond Light Source podcast.
The Diamond Podcast. For more information, look us up online at diamond.ac.uk/podcast.
The field of science can sometimes have a reputation for being quite clinical and methodical, but the subject requires a lot of problem solving and creativity, something which the team at Diamond are always keen to promote, as Silvana Westbury from Diamond's communications team explains.
Well, at Diamond we've done a number of projects that have brought science and art together. We've done things like Designs for Life, which was a textile project with the WI, and we've also had a number of artists in residence who've worked at Diamond, and that has all been really successful. So creativity is kind of in our blood. Obviously, it's in the blood of scientists who are having to be creative about problems all the time. So we thought it would be interesting to bring storytelling into the scene and to set people up to be creative in a storytelling way at Diamond.
And so that's why you did explore the area of storytelling, as you mentioned, with your recent light reading projects, which have been a range of projects.
That's right. And it was a little bit of an experiment for us. In the first instance, we just wanted to trial this idea and see if people would really be able to spend the time to, write a story. It takes quite a lot of effort and imagination. So initially we ran the competition for staff and we got a nice variety of stories, which I think really made us believe that this would be successful as a public competition. So about a year ago, we decided to launch the competition for absolutely anybody. So it was a public competition promoted via a website, special website, which was lightreading.org, held our breath and were absolutely delighted because we received an amazing range of stories. It was really great.
So, that was a year ago, and in the meantime, you've gone through the stories, you've selected winners and highly commended stories, but the main focus, I guess, is that more recently you launched an anthology of all of these top stories, which do touch on really different areas of science.
They do indeed. It's amazing. We've got romance, we've got crime scenes going on, we've got observing the synchrotron through the eyes of a cleaner there, and we've got discovering the synchrotron years after, and the people of the future wondering what on earth it was. There was a fantastically creative range of stories, really, really great.
And would you say these show quite a nice reflection on what life is like at Diamonds?
In some cases, yeah, although the winning story, which involved an alien, we haven't yet seen at Diamond. But the fact that people were able to almost get into the mind of a scientist and really describe what it's like to be so driven and so hardworking that, you forget your meals and all that kind of thing. I thought it was really, really great. People were able to describe scientists in a way that we could all relate to, even though they were not scientists themselves.
And I guess importantly, though, people can just access this whole anthology online.
That's it. So at lightreading.org you can read all the stories, and I would really recommend you to do so because it's really interesting.
And that website to read the now 25 published stories is light-reading.org, where you can also hear about Diamond's current story competition aimed at school children between 12 to 16 years of age, the deadline for which is the 8th of February 2013. Now, speaking of these fictional stories, we enter the world of a rather confused and worried scientist.
6 years ago, something happened. So small and insignificant I would not remember it if it were not for what came later. I could have just been tired, stressed, overworked. There was so much going on with Diamond becoming operational. I dropped a cup. Hot tea spilt on my trousers. Jill shouted, "Watch out, the carpet!" Our new carpet, bought to see us through. Spilt tea? There's nothing much in that, but this was different. I felt my hand slipping on the cup, but I could not make it grip. Soon it returned to normal. Weeks later, I noticed my eyes kept feeling tired, and they had an odd stiffness about them, as if my eyeballs needed oiling, and it took effort to look downwards. Months and months progressed, and with exciting developments at work, I thought nothing of it. Then I started to lose my balance, lurching oddly sideways or sometimes backwards, perhaps once or twice in a week. One day, Jill cornered me in the kitchen. "Go and see the doctor," she said. "All right," I said, sighing. "I'll go as soon as I can." I got to know Dr. Peter Marsh sometime that first year, the year I allowed myself to admit that I was ill. We still did not have a full diagnosis. A rare form of early-onset Parkinson-type dementia was all I'd been told. I heard from the control team that his research group were booked in for a series of time blocks using one of the X-ray imaging beamlines at Diamond. I was eager to talk to anyone researching degenerative brain disease to try and get some kind of handle on what was happening to me.
That was an excerpt from the story Things That Count by Rosalind Collette, whose tale takes a fictional and emotional look at a range of conditions regularly studied at the Synchrotron, degenerative brain diseases. One such scientist looking into this is Mary Finnegan from the University of Warwick, an engineer who's using her physical science background to take on the challenges facing this group of diseases.
So one of the main challenges with neurodegenerative diseases is early disease diagnosis and also accurate disease diagnosis. So with something like Alzheimer's disease, that's just the most common form of dementia, but it is only one of many forms of dementia. And it's very important to be able to diagnose diseases accurately if you want to treat them well. And at the moment, it's difficult to distinguish Alzheimer's disease from other neurodegenerative diseases.
I guess you also want to treat early, so if you can diagnose earlier, that would be great too.
Yeah, that's really important because in these diseases, cells in the brain are dying. So if you leave it late into the disease to treat the disease, a cell death has already happened and you're not going to get those cells back. So it's important to be able to diagnose early and start treatment early.
And so what aspect of Alzheimer's disease are you focusing in on? Because you're an engineer.
So we're using physics and engineering to look at the disease to help with diagnosis, and I'm particularly interested in MRI, brain imaging, and also interested in the metals that are changing in the brain on a cell level in the disease.
I guess because metals are naturally throughout our bodies and particularly in our brain, so what range of metals do we actually have here and what purpose do they normally serve?
So there's a large number of metals in the body and in the brain. One of them is iron, so people have probably heard of iron being in the blood, but it's also in the cells. It's really important in chemical reactions that happen in the cells signaling to each other, which you know is important in the brain. But it has also been considered a possible source of damage in the brain because it can cause this free radical production, which may be causing cell death and damage in diseases like Alzheimer's disease.
So what do you know so far about, I guess, the role of iron and cell death? Are there particular forms of iron involved, and what's known to date?
It has certainly been shown that there's increased iron in Alzheimer's disease in certain regions of the brain, and also increased iron in other diseases like Parkinson's disease in certain regions of the Parkinson's disease brain.
So what are you really looking into and focusing in on with your research here?
Well, I'm mainly interested in iron, and I'm interested in the increase in iron in Alzheimer's disease. And the main reason that I'm interested in iron is because iron influences MRI. So the changes in iron could be spotted with an MRI scan, hopefully early in the disease, and help with early disease diagnosis.
And so you're using Diamond to look into this. You're working with various brain tissues to look at iron levels. What are you really investigating, and how do you set about actually seeing the differences perhaps between Alzheimer's brains and regular brains?
So the first stage in my research doesn't actually involve Diamond, but it involves taking MRI scans of diseased tissue. So this is all human tissue that's been donated for research. So we do MRI scans of that tissue here at the University of Warwick, and then I cut it into thin slices. And it's these thin slices, these sections of tissue, that I take to Diamond to look at the metals at Diamond.
Well, so you've got a slide here, which has got some human brain tissue on it. So what part of the brain's on here? And tell me a bit about this slide.
So this is some sections from an Alzheimer's disease brain, and it's from the amygdala, which is known to be affected in Alzheimer's disease, and we should be able to see some of the pathological features of Alzheimer's disease on these sections.
Okay, so you're just going to stick that under the microscope now. Okay, and just looking down the eyepiece now, there are what am I seeing here really? So what I can see is kind of a beige colour with lots of brown dots on it.
So the little spots, which should be a kind of purpley colour, they're the cells. So some of those cells will be neurons and some of them will be glial cells. And you should also be able to see this kind of larger red stain.
Oh, yeah, just towards the side.
Yeah, and that's actually a stain called Congo red, which is staining a protein called amyloid, which builds up in plaques in Alzheimer's disease.
And so what can you see from this, perhaps, about where you might want to look a bit more closely for, say, iron levels and so on?
So what I would have done is I've taken some sections and I've stained them like this so we can see the proteins, but I've also taken some sections and kept them very clean and put them on a clean slide, which we take to Diamond to look at the metals. So by comparing one of the stained sections with one of the unstained sections, I can pick an area where I know the disease exists in the tissue. Then I can look at the metals in the adjacent sample that I haven't stained.
And which beamline are you using, and what do the X-rays say really enable you to see? What do they show?
So we're working on I-18 beamline, and the X-rays there, we can tune the energy very specifically. So we work with X-rays at 10 kiloelectron volts, and we can also focus the beam size to different sizes. So we can work with the beam size very small, maybe at 3 microns, and that allows us to look at metals at a resolution that allows us to see the metals within a cell. But we can also make the beam size bigger, so maybe 60 microns, and that allows us to look at a bigger area, so we can look at a larger piece of tissue and see how the iron changes across that piece of tissue.
Okay, and well, you've got a picture just up on your computer screen of one slide where you've done this, and there's lots of different colours going on, a bit of pink and a bit of green. Which of these is the iron?
We use a detector that can detect different energies for X-rays, and we know that iron gives off a particular X-ray. So then we take those X-rays and we effectively colour them in red, and we colour red for iron, green for copper and blue for zinc, and then create a map where we can overlay these different colours.
And with your samples so far today, what have you really seen? So I guess are the areas affected by Alzheimer's, so I guess places like the hippocampus to do with memory and the amygdala, which you've got on a slide here, do these areas have more iron?
With my research, I haven't completed all of the analysis yet, but I have observed increased iron in some regions of the brain which I haven't seen documented in the literature before. So I've looked at a number of different regions of the brain where in the literature there's been some evidence for increased iron, and I'm doing MRI of all of these regions and then this iron analysis, and I'm hoping to see changes in the MRI and also in the iron that would then highlight particular regions which might be useful to look at in a clinical study. So this is kind of preclinical work which might later on inform a clinical study with MRI scans of living patients and compare between disease and control.
So would it really be, I guess, ideally a way so that if patients are exhibiting any kind of early symptoms, that this would be a way of an MRI confirming that it could be leading to Alzheimer's? Yeah,
that's potentially the idea behind this. It would find some markers in the brain that you could look for when you would see an early change in the MRI in a patient, and that would be something that you could use to then say that they would be going on to develop Alzheimer's disease in the future.
Mary Finnegan from the University of Warwick.
Did you know that Diamond's floor-level monitor system shows Diamond tilting twice a day due to the moon passing overhead?
You're listening to the Diamond Light Source podcast, and this month we're opening up the books and entering the world of fiction to see how science and storytelling collide at the Synchrotron. Still to come, we hear what might happen if a disease were to outbreak at Diamond, and how probing down to the molecular level is helping in the fight against plant pests and pathogens. But first, we join Silvana Westbury once again for a roundup of this month's news.
Increasingly, the synchrotron's being used by scientists who are looking into solutions to the many energy and environmental issues the world is currently trying to address. And one example of that is scientists from the University of Oxford and Diamond have described a new chemical catalyst for producing methanol, which is a promising future biofuel. By reducing the energy needed to convert biomass to methanol, the new catalyst offers a more sustainable way to make the useful chemical and fuel.
So why do we even want methanol, though? Why is it useful?
Well, at present, methanol is used primarily in industrial chemistry, including the manufacture of plastics and synthetic fibres, and as a fuel in fuel cells. It's manufactured from natural gas, a fossil fuel, but some biotech companies are now in the demonstration phase of synthesising methanol from biomass waste, such as agricultural residues and wood chips.
So, if this process is already happening, what are some of the limitations for the need to, have new methods of making this methanol from biomass?
Well, the current method of producing methanol from biomass is hugely energy intensive. That's the problem. The tough cellulose in biomass requires high pressure and very high temperatures of about 800 degrees Celsius to be broken down into carbon monoxide and hydrogen, called syngas. These basic molecules are then reassembled to make methanol. Creating methanol directly from biomass molecules would require much less energy, which is what this new catalyst offers.
So really cutting out this middle energy-intensive process. Are there already processes out there to try and skip this step and create methanol in a different way?
There are. Catalysts already exist to convert cellulose into ethylene glycol, the chemical in antifreeze. Now, the palladium-ion catalyst developed by Edmund Sang and colleagues at the University of Oxford, it actually bridges the second half of the gap, transforming that ethylene glycol into methanol.
So what have they shown about their palladium-ion catalyst?
So their findings, which have been published recently in the journal Nature Communications, actually show that the catalyst has high selectivity, meaning few chemical byproducts and more energy efficient conversion.
And do they know how it works?
That's the mystery. So to find out, the researchers turned to Diamond and to our X-ray absorption spectroscopy beamline, and they found that the reaction with ethylene glycol had induced small clusters of palladium and iron to form on the catalyst surface, and that it was this chemical combination that worked the trick. Knowing this will allow the Oxford researchers to further tweak their catalyst to improve its efficiency and specificity.
Okay, well, as well as creating new fuels to get us out of the current energy crisis that we're in, there's also been work at Diamond to try and ease the damage from our current reliance on fossil fuels and reducing the levels of carbon dioxide in our atmosphere.
That's right. So this is really exciting. This research is about a new porous material, which has been dubbed NOT 300. It's actually got the potential to reduce fossil fuel emissions through the cheaper and more efficient capture of polluting gases such as carbon dioxide and sulfur dioxide. This research made the cover of the journal Nature Chemistry.
So this is really reducing the levels of carbon dioxide in our atmosphere by capturing it, really, and stopping it actually being in the atmosphere. Who's been working on this?
So this is a collaboration between the University of Nottingham, STFC's ICIS Neutron and Muon Source, Diamond, the University of Oxford and Peking University in China. They've created this new low-cost material that can capture harmful gases.
So how does this material really work and what's it made of?
It's made from aluminium nitrate salts and cheap organic materials, but also only uses water as its solvent, so it's non-toxic and requires less energy to strip out carbon when it becomes saturated.
And where would it really be used to do this stripping of carbon dioxide?
It's got a lot of applications, but it could be placed in industrial power stations on their flue gases, which are mainly CO2 and SO2. So NOT 300 could strip the CO2 to stop it being released here, and it can also act as a filter on natural gas, which currently has 10% CO2 in it, to take that polluting gas out.
So two new ways really to try and improve our kind of energy situation at the moment. But as well as research, Diamond does have a lot of outreach related things going on, including your open days, which we always mention on the podcast. So when's the next one?
Well, the ever popular Inside Diamond Days, the November day is all fully booked. So I wanted to let you know about the next opportunity, which is Saturday, the 12th of January, 2013.
And soon after that open day, Diamond's heading overseas to America for the AAAS Science Conference.
That's right. So we're very fortunate to have had a symposium selected for the AAAS in February, and it's going to be titled The Invisible, Revealing the Dangerously Beautiful, and we'll be particularly focusing on our life science research and particularly some findings that have been made recently relating to viruses.
So join us next year to find out how it goes. That was Silvana Westbury from Diamond's communications team. Sticking with recent research news at Diamond, the 1,000th protein structure was recently identified on site and offered hope for improving the health of our crops in the future, as Mark Banfield from the John Innes Centre in Norwich explains.
So this was from a protein called ABR-RPS4. It's a protein from a particular pathogen called Pseudomonas syringae, pathobar pisci. So this is a pathogen actually of pea plants.
And so what protein have you really identified here, or what kind of structure have you found, really?
The structure of ABR-RPS4 is a alpha helical coiled coil. It's an anti-parallel alpha helical coiled coil. So we start at one end of the protein and we go through a secondary structure unit called an alpha helix, which is a very standard structure that's found within proteins. And we go up to the top of the molecule and go around a short turn and then come back down the other side. And in essence, it's a very simple protein structure. But nevertheless, it's a type of structure that is found in a wide variety of different proteins and can deliver different functions.
But what's the real kind of role of this protein? So how does it help, say, pathogens kind of infect a plant?
With this particular protein, in fact, what we were aiming to look at is what's known as the recognition event in the molecular warfare between the plant pathogens and their hosts. So we don't actually know why the particular pathogen is secreting this protein and injecting it inside its host cells at present. Now, we know this protein is translocated from its bacteria into the host, but we don't actually know why the bacteria is doing this at present. What's been interesting about this protein to date is actually the way in which the plant host recognises the presence of the protein inside its cells. So this is where the phrase RPS4 comes from in the protein's name. So ABR-RPS4 stands for avirulence protein recognised by RPS4. And RPS4 is a plant immunity protein that's present in the cytoplasm of the plant cells that are being infected.
And so by knowing how this plant, say, sees this protein coming in, are you wanting to see how it builds up a defence against it?
Yeah, so RPS4 is a member of a large family of proteins that are present in plants called resistance proteins. And these resistance proteins are there to recognise the presence of pathogen proteins that have been injected into the cells or have been translocated into the cells by the pathogens during the infection process. What normally happens in these processes is the resistance proteins will recognise these foreign proteins inside their cells that have been delivered from the pathogens, and they'll then respond through this immune system very strongly, actually causing cell death.
How important is, say, knowing the structure of the proteins, I guess, in this whole identification of this process? Because we are celebrating the fact that Diamond helps actually see structures of all of these different proteins. And why is it important, really, to know the physical structure of them?
So one of the key things that's not understood at the moment is the molecular recognition events that occur within inside plant cells when a resistance protein such as RPS4 recognises the effector protein, of which ABR-RPS4 is one, inside the plant cell. Understanding the molecular details of how these resistance proteins recognise the plant pathogen effector proteins, that we can look towards at least engineering new varieties of plants that can recognise diverse range of pathogens, and these resistance proteins could then be transferred into crop species that can then resist a wider range of pathogens in the environment, for instance when they're grown as crops in fields.
Mark Banfield from the John Innes Centre in Norwich. Now let's step away from research and delve back into the world of fiction, where an outbreak of disease may have just occurred.
I don't know how long I have. My name is Natasha Coles, and I'm a consultant in tropical medicine at the Oxford John Radcliffe Hospital. I'm recording this to get 3 very important messages out. Message 1, this virus, disease, whatever it is, it has other transmission vectors, other than human bites. Being scratched is one. It might be airborne, but I don't know that for sure. I really hope not. Message 2. Along with this recording, there are a series of data files from the beamline at Diamond. It was a hell of a job, but we imaged it. I'm praying that the information in those files will help us to determine what you're going to be dealing with, and maybe find a cure. Message 3. Maya and Ben, Mummy loves you now, and always will. I'm sorry, I can't say goodbye in a better way. My darling Steve, being with you was the best days of my life. I love you all. The warning: Diamond has been infected. If the transmission vector is only bite or scratch, then I think it's contained. If it's airborne, be prepared. Everyone on site will have been exposed. This is not a hoax. Good luck, and God have mercy on all of us. Message ends.
You can find out if our character was right, as well as discover who did and didn't survive the outbreak, online at light-reading.org. That was an excerpt from 28 Hours, a story highly commended in Diamond's light reading competition. Written by Sarah Callahan, pen name Saoirse McCall, a former researcher in radio communications, who now works in data management on site at the Rutherford Appleton Laboratory. She describes her inspiration for the tale.
The story came about as a result of all the kind of zombie stories that are going on at the minute in television and films and stuff. Now, I don't like zombie films myself. They scare the living daylights out of me. But one thing I've noticed in science fiction, especially in TV, is the stories that tend to get told tend to happen 6 months or a year after a big apocalyptic event, like the zombie plague outbreak. And I wanted to take it back to those few hours or possibly even a day after the first outbreak to investigate and to think about what sort of things people would do and how they'd react to it in those very first few hours.
And so how did you set about researching this, and how did you really set it at Diamond as well? Well,
I'd had the chance to go and have a look around Diamond on a couple of their open days back when they were actually building the whole facility. So I had an idea of what was going around in Diamond, or what it was like actually being in Diamond itself. And then I went and had a poke around the Diamond website and saw some of their news items where they were talking about how they use the Diamond beamlines to investigate the structure and shape of biological samples like pathogens and viruses and the like.
Your story really then uses this as a kind of race against time to kind of diagnose and see the structure of this pathogen.
Pretty much, yes.
By putting together this fictional tale based there, has your perspective or view of Diamond changed at all as a result?
No, not really, although I did, as part of the prize-giving ceremony, we did have the chance to actually go on a tour of Diamond again, and I found that fascinating just to see how much things had changed, because the previous tour I'd been on was when they had just finished building the storage ring, so there wasn't all the stuff, all the beam lines set up, and there wasn't all the equipment there in operation and in use.
Light reading writer Sarah Callahan. Now, that's almost it for this month, but before we go, we continue our celebration of Diamond's 10-year anniversary with a perspective from one of the designers of the Diamond Light Source building itself.
Hi, I'm Crispin Ride, architect designer of the Diamond Light Source facility near Oxford. When we won the design competition for DLS, it came at a particularly opportune moment when another of our projects had just been put on hold after 9/11. DLS was an exciting and complex new project for us and involved a broad team from our architects and structural environmental services and geotechnical engineers through to the DLS team of scientists designing the machine itself and the users with their specific requirements. It was particularly fascinating for us to peer into an alternative scientific world, and one with which we wouldn't normally have any access. The brief set us a series of challenges requiring a solution that was practical, but with a strong identity to reflect the cutting-edge science within. Surprisingly, the futuristic spaceship identity that we opted for was welcomed by the planners, so much so that they even asked us to reduce the landscaping around the building so that it would be more visible. In the early discussion, it was clear that the scientists were working to a much higher level of precision than was normal in the building industry, and therefore we worked closely with DLS to understand the machine's operational criteria, but also to make the building both easy to construct and cost-effective. Concepts of tolerance varied wildly between the scientists and the contractors, and we acted as mediator, marrying together the two sets of aspirations. To have a brief that demanded a circular building was very unusual. The building was simplified to a 96-sided form, with each of the faces 7.5 metres long. The external protective solar blades providing the vertical curved appearance and creating the unusual toroidal form. The scale of the building allowed the external wall to be constructed as if it was straight, and I remember in the very first presentation suggesting that it was therefore, to all intents and purposes, a building without any corners. The retort from DLS was to the contrary. The building was in fact just one big corner. I suppose it's all a matter of perspective.
Crispin Ride from Jacobs Engineering Group. Now, that is it for this edition of the podcast, but make sure you join us at the end of the year as we look back at the research highlights of 2012. In the meantime, if you have any questions about Diamond or the research taking place there, the email address is podcast@diamond.ac.uk, or you can listen to the previous editions of this programme online at diamond.ac.uk/podcast or nakedscientists.com/diamond. You can also subscribe to the podcast on iTunes. Thank you this month to Sylvana Westbury, Mary Finnegan, Mark Banfield, Sarah Callahan and Crispin Ride. I'm Mira Senthilingam, and until next time, goodbye.
The Diamond Podcast is brought to you by Diamond Light Source and produced by thenakedscientists.com. There's more information on our website at diamond.ac.uk/podcast.